And today's session is the first in a series of webinars where we're going to be diving deep into the hot topic of EMI. So stay tuned for invitations to the next couple sessions in the series. Now, our speaker today is Christian Kueck. He's a senior FAE based in Germany, and he has such strong experience with EMI that he's built his own test setup at home. You'll see a couple of videos from that. Now, Christian's presentation is going to run about 20 to 25 minutes, after which he'll address any questions from the audience. We invite you to submit questions via the Q&A option that you'll find in your Zoom controls, and we will, again, address these at the very end. So now, without further ado, I'd like to turn it over to Christian.
Okay, so my name is Christian Kueck. I am for a long time senior FAE for 22 years at Linear Technology, supporting mostly automotive customers, and now since 3 years at MPS. And always a good part of my work was fighting EMI, especially in automotive environment, which is a lot harder than in the industrial environment. And today my task is to demystify a little bit the myths about EMI, because EMI is in lots of cases not intuitive, and I want to go today in some details about that. As Alan said, if you ask questions, just put them in the Q&A form, and after the main session, we will go over your questions. So first we will analyzing a typical power stage on a non-isolated DC to DC converter, which is the mainstay or most often used in automotive. We will see a magnetic coupling and demo videos to that. We will discuss key loops. We will go to layout hints, and then we go to your Q&A. Okay, if you go to a typical power stage, first what we have is a schematic, and from the schematic most times you have problems identifying what are the critical components and critical loops are. So your schematic will show on a step-down converter like the MP or MPQ 4430 an input decoupling network, so input capacitors which go to switch node and go to power ground, but it's not really obvious how that needs to be connected. And all these components which are hooked up to that circuit will have parasitics. Now, so it's quite obvious that the input capacitors, inductors, and so on have parasitics, and they are usually fairly well known. MLCC capacitors have easily 4 nanohenry ESL and 4, 5, 10 milliohm ESR, and also these parasitics could be simulated. So that isn't a big surprise. But the parasitic elements are still in concentrated components. What we usually don't take into account is that the PCB has resistance and even more inductance. That would be a lot harder now to integrate that in a simulation. Or what we should keep in mind, that traces will have resistance and will have inductance. And what most times is seen is that all the components and all the traces don't have a physical size of 0, which means that they will have capacitive coupling and also inductive or transformer coupling to each other. And that's usually will be beyond the scope of, say, a simulation tool that can make a complete simulation of all the coupled inductances and coupled capacitances. However, that are typically on EMI, as we look for higher frequencies, the biggest problem. So in reality, we would have to add subcircuits for all nodes, and that all nodes talk to each other via capacitive and inductive coupling. If we talk about E-field or capacitive coupling or near-field coupling, we can assume now that the components will give capacitor plates which talk to each other, which form a capacitor, and over these coupling capacity or E fields, they will couple. And typically, as larger those components are, as higher they are above PCB, and as closer they are, as higher the coupling capacity. In addition, through every part where a current flows through, we will have a magnetic field, or create a magnetic field, and this magnetic field will transform, couple into other components, would also rise above the PCB excuse me, in a magnetic way. So we can think that the parts transformer couple to each other. For magnetic fields, I will come back to that now. Currents are necessary. So the only thing which create a magnetic field will be a current, and as higher you rise the current above the PCB, and as further these magnetic fields will reach. These additional coupling mechanism would be right-out electromagnetic wave creation, like an antenna, so that you have parts which create an electromagnetic wavefront and couple directly like an antenna into the other. But for that, it's necessary that the component size has to be in the order of the wavelengths, so lambda divided by 2 or lambda divided by 4. Most times the parts are pretty small. We use against the wavelengths we are interested in. Typically for a DC to DC converter, the energy falls off in the 700 megahertz range, so you won't have any energy above a gigahertz, and for gigahertz wavelengths would be 30 centimeter in free air, so normally you don't have such large components. But if you have wires or larger areas, PC boards also, you will also sometimes see that you emit directly electromagnetic waves. Keep in mind now that the epsilon R of an FR4 substrate is in the order of 3.8 or 4, which means now that that reduces the wavelengths by a factor of 2. So effectively, you need smaller components. Okay. So there are lots of influences, so it could be hopeless, but it's not, because not all effects are relevant in all components. And so we can reduce usually the components and the circuits to the ones which have the dominant effect in non-isolated DC to DC converters. If you go first to capacitors, I got from an old TDK tool here the impedance over frequency of an 04 or 2 capacitor in 100 picofarad, 1 nanofarad, 10 nanofarad, 100 nanofarad. And you will see that in the area at least below 10 megahertz, they're all nice capacitive. To certain points, they have a series resonant frequency, self-resonant frequency, where the parasitic inductance, which the body shapes with the capacitance, form a resonant circuit, and there's actually the impedance at a minimum. And on the right side, you will see the inductive effect now, which will be created only by the body size. Now you could think for the inductive effect that you replace the ceramic capacitor by a copper block of the same size, and you will see that all the 0402 capacitors at high frequency above 1 gigahertz have pretty much the same inductance. You could think now that above the self-resonant frequency, the parts become inductance and doesn't bypass anymore. But that's not the case. Only the phase shifts over 180 degrees. So it will be an inductive component, but it still be fairly low impedance. So if you look for the 1 ohm line, even an 100 nanofarad capacitor will pretty good decouple at 300-400 megahertz. It will form at least an inductive 1 ohm short circuit. So even in the inductive area, as long as the impedance is low, they will still be a pretty good bypass element. On the magnetic coupling, Typically, capacitors are mostly magnetic coupling elements because they have AC currents, so that's their job to decouple voltages, make voltages stable. In order to do that, they have to conduct AC currents, and these AC currents create magnetic fields and they transform a couple. And that's a wideband coupling path now easily to the gigahertz range. And that if you place them close to together and they form say two transformer winding, that often defeats their filter function if it's, for example, filter capacitors. Keep in mind that electrical fields are created by voltages, and we are not interested in DC voltages, AC voltages, what's count. Magnetic fields or fields are created by currents, and currents always flow in closed circles. So they never end up in a ground plane or an alien flower pot or whatever, but they will go through the ground plane or to the plane back, and you will always be able to identify the full circle if you look a little bit closer. Okay, for magnetic coupling, I made a demonstration video. I started with the 4430 step-down regulator. Here on the left side, we see a symmetric VIN decoupling. In order to make it a little bit easier, I removed the top VIN decoupling capacitor so that we have only a single large MLCC VIN decoupling, the 100 nanofarad one. That's the part that's VIN trace. Here, that's the ground area. The inductor, actually, I placed on the back side. Now, so I drilled holes through the board. Now that the inductor is really on the back side to get rid of the electric and magnetic field from the inductor. Just want to concentrate here on the magnetic fields on the MLCC and the other parts. And here that are the output capacitors. The layout of this 4430, which is an automotive 36 volt amps max, 3.5 amp step down regulator, which can go up to from 250 kilohertz to 2.5 megahertz if you want to. We made for the demo board a 4-layer layout. Now, so here you see the input traces, the in traces, symmetric decoupling. Next layer is pretty much all ground. On the third layer, now there are some sync enable signals also routed, and the fourth layer is also ground, and we place the EMI filter on the fourth layer on the back side or on the bottom layer. The schematic we have already shown, as there are input decoupling caps. Now we removed, I think, C1A. Now we have C1B and these smaller capacitors. And we have on the back side an EMI filter. Typically, we use a fourth order EMI filter with 2 inductors. To get a realistic picture, what a capacitor, an MLCC capacitor will pick up, I made actually a probe out of an 0805 MLCC capacitor, soldered in it to a small RG316 coax cable, and have the ground return or the return here from the shield with that small copper wire. Now, so I made a pickup from a capacitor. I will move the pickup, that's a probe, now over the PCB. And first we will concentrate here on a frequency range up to 30 megahertz. Resolution bandwidth is 30 kilohertz. Here we'll see the input voltage, input current, output voltage, and output current. Okay, now, so let's start the video. Now you will see if I dial up the output current, now the pickup is placed close to the input capacitor. It will come up proportional to the current. I'll dial up the current to about 2 amps. Now you see a nice fence or comp signal, And as further I move the pickup away from the input capacitor here on the side, now as lower the emission or coupling is. So if I place them close together, I see a lot of coupling, and as more as more distance I have to the input capacitor and to the hot loop, now as less coupling I get. Oh, I check on the output capacitor or near the output capacitor. That's not very much now on this side, even if I go close. We'll see a little bit low frequency content as we could expect on a buck regulator, but not much. Or to the other side, which is a little bit closer to the switch loop here, and we will see more, as we can expect. And if I look almost by 90 degrees, now it's also not very much. Now, so that's also a trick you can use if you place capacitors 90 degrees to each other. Now you reduce the magnetic coupling. Okay, so we have the same setup, but now we look for frequency range up to 300 megahertz. The resolution bandwidth will be 120 kilohertz, now, so it will be a little bit slower for the EMI receiver, for the spectrum analyzer to go through the complete field. And we place the pickup close to the input capacitor. We see now that the EMI in general goes up, and as further we are away from the input capacitor, now as lower the magnetic field is, and we pick up with our probe. The coupling to the capacitor. Output, if you look close, that's a little bit astonishing now that in the frequency range around 200 megahertz, you will still see some energy on the output capacitor. Reason is now that the isolation of the inductor is not perfect. Now there's always some parasitic capacitance of the main inductor, which shoves a little bit energy through. Okay. Now the question is, why is the magnetic field amplitude at the bandwidth so much higher on the input bypass caps now than on the outputs? Now, why is so much more energy there? Now, so let's discuss the key loops in a buck regulator. If you have a buck regulator, we can reduce the whole AC path to the input capacitor, top switch, bottom switch, inductor, output capacitor. Over the inductor, we have a triangular waveform, and on a triangular waveform, shape is already pretty close to a sinus, the harmonics will go down with the square of the harmonic number. So the second harmonic will be divided by 4, third harmonic by 9, fourth harmonic by 16, and so on. So it's not a really wide band signal, but the current through the top switch will be mostly of a rectangular waveform, at least with an inductive slope, but it's fully switched. So in the top switch, and with that also in the input capacitor, you will have a fully switched waveform. On the bottom switch, the same. Now you get also fully switched waveform. It will be the other current, but you still have a pretty much rectangular waveform. And on a rectangular waveform, the harmonics decay only linear with the harmonic number. So second harmonic divided by 2, third by 3, fourth by 4. So it's a much more wideband signal you create there. So you can think now that the converter hot loop or the loop where we have very high DT. The fully switched loop consists out of the input capacitor, the top switch, and the bottom switch. Now that we are calling the hot loop. And think of that, the hot loop is a fully switched current. So we create actually a magnetic dipole antenna. And every trace on your PCB which transports AC current actually makes a magnetic dipole antenna or a magnetic antenna. And the radiation performance will depend on the current, on the input switch current. Usually we can't do much now, because if you have to make a 2 amp or 3 amp supply, we get 3 amp switched. But also the radiation goes up with the area. So current we have now, but it also goes up with the area. And the area is a parameter on the layout. We can do something. So in order to reduce the effective magnetic energy transmitted, now we should make the area of that hot loop as small as possible. Now let's think about current flows in a PCB trace. We have now a cross-section of a PCB, and I look directly into a PCB trace and think about highest frequency current, 100 megahertz and above. If I get current through this copper conductor, the current will really gather at the outside due to its skin effect. You can think now that current going through an conductor always tries to minimize the magnetic field inside of an inductor. No magnetic AC field inside of an inductor or conductor means that there can't be current density inside the conductor. So the current density will gather at the outside, and that's called skin effect. If you have a top conductor on our PCB, and here we have some isolation, and we have in the second layer, for example, a plane, ground plane, for example, and the current goes in the conductor in this direction, comes back in the ground plane. We have opposite AC current directions, and opposite AC current directions, actually current density will attract each other. So the current density in this top conductor will attract the return current in the bottom conductor in the ground plane. So most of the AC current will flow directly under the top trace. And even if you have more layers and have, for example, several layers of signals separated by planes, then the return currents will concentrate under their conductors, and you will actually get a pretty good isolation even in the solid copper conductor now, because the high frequency currents really gather under their top traces or bottom traces in this case. If we think about the hot loop of a DC-to-DC converter, we usually have the loop current flowing in the top trace, one in this direction, and since it's always a closed loop, we have also opposite direction. Also, the current density between these two wires will concentrate here at that area because we have opposite current. And we have, if we have a ground plane underneath, we will get an eddy current here, which will be opposite to the top one, and that also in addition concentrates the current. So most of the current concentration on a loop on the top trace, where we have a solid conductor like a ground plane under it, will concentrate here where the current in this direction finds its backflowing current. And also it concentrates here because I have here opposite eddy current going. I still have a little bit current density at the outside from the skin effect, and we will come later to it, why that's also can be a problem. We can make a clever layout to reduce its radiating effect. So for any given aspect ratio, what you should try is to make the distance or the dielectricum in your PCB as small as possible between the plane and the top conductors. You can go, I think, as low as 75 micrometers. So typical 4-layer board would be 200, 250 micrometers. If you want to go lower in EMI, if you can from the voltages, sometimes preferable not to make the distance here smaller if you can. To show the effect, I made actually a video using an induction stove. Now, let's see. Induction stove actually works with about 22 kilohertz, which is an AC frequency, which is quite low, but it's still pretty indicative what's going on. So I have a loop where I pick up the main current from the induction stove that it's operate. I have to put a water pot isolated on it. And if I switch it on, I will get about 100 amps AC current in that rectangular loop. Now I place on top of the loop an aluminum foil, and if I switch it on, the aluminum foil will fly because it creates eddy currents. And if I put a ground plane or a current conducting plane under it, actually it will reduce the height of the aluminum foil, which indicates that the eddy currents are lower. Now if I have an conductor. Same from the top side. Now it really doesn't matter if I come from the bottom or the top side. I will reduce the eddy current in the aluminum foil if I have a plain conductor below or above it. And that we can also use if you make PCB boards. So try to make under your hot loop a solid plane as good as possible. So eddy currents can cancel the original magnetic excitation fields, and they do it better as close as the conducting plate is to the original conductor. And that means also that this cancellation of any plane, maybe ground plane, works better with low profile components, flat, short, and wide. And the plane we put under our top trays should have no gaps and holes and vias and these things. It should be as solid as possible that I can create an as original picture of the top current for the eddy current as possible. And with that know-how, now let's go to the layout hints for non-isolated DC to DC converter. I have here a pretty old DC to DC converter, which is non-synchronized. So I have a top switch and a bottom switch. Doesn't matter if the bottom switch is a diode. Now the hot loop still consists of the input capacitor, top switch, bottom switch, or diode. Now, so that's the hot loop where the highest DI dt is. Now, so it would be here in our layout. That's the VV input MLCC capacitor, the in trace. Now here's that's a switch node. Diode. Now, so that's the inductor. Now, so we have to make sure that here under this area there should be a pretty solid ground. So back to our 4430 and the second layer, we try under the hot loop now, which is here, to make a solid plane on the second layer now, and don't make any holes in that area. And that would be solid. Input filter components. Now we talked a little bit earlier about a transformer coupling of MLCC capacitors, and you can, for that reason, we try to move the capacitors as far as away from the main capacitor and the main inductor. Now, so we typically place the filter on the backside of the PCB. Now, so even if you can't do that, make your filter as far as away as possible from your main DC to DC converter, which is here on the back side. Also make a little bit more space between these inductors now, because they also talk to each other. That's actually not a very good example. That's an older layout what we have. And also the capacitors of the direct input and the intermediate stage here now should have some distance. What we found is now that usually fourth order EMI filter using two inductors perform better because you can reduce the component size and especially the height of those components drastically and get the same filter effect. So for less area, less volume, less money, you get better filter effect for the simple reason that it's physically a lot smaller. Okay, now let's talk a little bit about EMI measurements. Radiated EMI is measured with antennas. Conducted is measured with Lesion, not directly here. And between radiated and conducted, you will see significant differences only in the, say, few 0 to single-digit megahertz region. If you're talking about 30, 100, or 300 megahertz, then whatever radiates will also actually radiate into these wire, create common mode currents, and at the end now will find its way through the lesion, and you can measure them also voltage-wise. So up to a few megahertz, typically current sticks to its wires, sticks to the SPICE circuit. So if on the fundamental and the first few harmonics you have a problem, you can directly play with your EMI input filter. But for higher frequencies, we have the coupling effects transformer and E-field coupling, as we had already discussed. Switching frequency. Very often I ask, okay, what's the best switching frequency? And on automotive, lots of people like to run them above the AM band, so then they don't have to think about AM radio interference. However, there's one physical problem. If you double the switching frequency, you double actually the EMI energy, because you go twice, 2 times as often through the edges, and that means that you get at least 3 dB more energy. Now we are talking about energy. However, the next problem is that with doubling the frequency, you only have on the spectrum half the bins where all this energy gathers. So for 500 kilohertz, you have these bins. For 1 megahertz, you have only half the bins, which means in addition to the 3 dB more energy you create, due to the fact that you have only half the bins, half the area where this energy concentrated, you get an increase of actually 6 dB. So doubling the frequency means 6 dB more EMI everywhere, which means if you go from sub-AM, like 500 kilohertz, to 2 megahertz operation, you get at least 12 dB more EMI to fight off. You might get a little bit back now if you go to spread spectrum technologies, but the 3 dB you will even go with spread spectrum. So for the first stage, it's not always a good idea now to go to really above AM frequencies. For the second stages, maybe 3.3 down to core, or 5 volt down to core, that's very easily can go above AM and run at 2 or 3 megahertz, because you're already behind the EMI filter and behind the first DC to DC converter. But the first DC to DC converter, which is hooked to the car battery, I would usually recommend to run at sub AM if it's in the several amp range. Okay, so what we learned today: make your hot loop small as possible, place a solid ground under the hot loop, under the EMI filters, inductors. Use a multi-layer board with thin dielectric between the top and the next ground or eddy current conducting layer. Use force order EMI filters, because for the simple reason the components are much smaller for the same or better effect. So you can use flatter components, smaller components which talk less to each other. Use switching frequency at least for the first stage, for the 14 volt or 12 volts down stage, not more than necessary. So for in the above 1-2 amp range, I'd recommend to stay sub AM. Even so, we make most of our switching regulator, which can go below AM and above AM range. EMI will hurt you. For the POL stage, it doesn't matter, because they are have smaller voltages and are already behind the first stage. For troubleshooting, use near-field probes. I made a probe myself here out of an 0805 capacitor, but there are special magnetic and E-field probes from the usual suspects like Langer, Rode and Schwarz and so on, you should use for EMI troubleshooting. And above a few megahertz, you won't find your EMI problems in the schematic. So very often you think in schematic and think, okay, I increase the capacitor here, add something here. And most times you get the opposite effect. And I hope today you learned a little bit now why it is the case. And look for magnetic and electric field coupling. Further support that now here, MPS builds up EMI test centers. We have already one in Hangzhou, and additional labs will be built in Detroit, Germany, and Shanghai. So that's with the presentation, and now I get to the Q&A sections.
Okay, thank you so much, Christian. Folks on the line, if you have any questions for Christian, now is a great chance to submit them. You'll find the Q&A option inside of your Zoom menu. And Christian, looks like we have one question on there.
Yeah, okay. Output capacitor should be placed 90 degrees to each other. Your EV board does not follow this. Can you clarify? First of all, output capacitors, they should be placed away from the input capacitors. You can be, because the input capacitors on a buck regulator have the highest DIDT. If you would go to a booth, it would be the other way around, but no matters less. So if, for example, the layout forces you to make them the input capacitor close to the output capacitor, you can put the output capacitors 90 degrees to the input capacitors. Our EVBs sometimes do this. Sometimes there's so much distance that you don't need it. And a lot of times, EVBs were made at a time where they weren't optimized for automotive EMI. So if you get an automotive switcher from MPS, there most times now we have also already an automotive optimized EMI optimized layout, where we try to make the layout as low EMI as possible, and usually the system 25 and the OEM specs. However, there are older boards now which sometimes from EMI standpoint are suboptimal. Okay, there are other questions, or is this a question answered? Okay.
Okay, so it looks like no further questions, in which case we'd like to say thank you to everybody who's attended today. We will make this session available for offline viewing later, and we'll send out a link to be able to access the presentation in PDF format as well. So again, folks, thanks for joining today, and stay tuned for an invitation to the next version of this EMI webinar series. Have a great day. Thank you.